Black holes eat information. Quantum mechanics says information can never die. Both cannot be true. For 40 years, physicists called it a paradox. Then in 2014, researchers discovered that black holes behave exactly like quantum error correction codes. The same mathematics, the same structure. Nature was already running the solution. This is not speculation. This is documented science with names, dates, and numbers that changed everything we thought we knew about reality itself. Physicists looked at quantum gravity through every lens they had. String theory, loop quantum gravity, mathematical frameworks that filled journals. Nobody saw the pattern until they stopped looking at gravity and started looking at how information survives errors. This script is researched and factual, using sources from the journal NPJ Quantum Information, published January 10, 2025, where Yoshida and collaborators demonstrated explicit decoding circuits for the Hayden-Preskill protocol, and from the European Physical Journal C, dated May 20, 2022, reviewing holographic spacetime and quantum error correction frameworks with extensive field theory analysis. These are not popular science summaries. These are peer-reviewed technical papers with equations, proofs, and experimental protocols. Now back to the information. If a black hole forms from a collapsing star and then evaporates, every detail about that star vanishes. Quantum states erase. Information dies. Hawking called it particle creation. The physics community called it a bomb. Take a book and burn it. The information in those pages does not disappear. It spreads into smoke patterns, heat distribution, ash structure, photon trajectories. Recover those, and you rebuild every word. Difficult in practice, guaranteed in principle. Black holes seem to break that guarantee. But Hawking's calculation was ironclad in its framework. Curved space-time, quantum fields, semi-classical approximation. The radiation came out thermal, and the information stayed dead. Except one thing bothered Page. What if you track not just the black hole, or just the radiation, but both as one entangled system evolving together? First paper in September. Second in December. He lacked the tools for a full quantum analysis, but he made one powerful observation. If a black hole starts in a pure quantum state and evaporates unitarily, the entropy of the radiation must follow a specific curve. Start at 0, rise as particles escape, peak at the halfway point when the black hole has radiated half its initial entropy, then fall back to 0 when evaporation completes. This is the Page curve. The peak moment is the Page time, roughly half the black hole lifetime. The black hole and radiation transition from independent to entangled to unified. The curve captured what unitarity demanded, but the mechanism remained invisible. The large N limit of superconformal field theories and supergravity. Inside was a revolution. He showed that a theory of quantum gravity in 5-dimensional anti-d Sitter space is mathematically equivalent to a 4-dimensional conformal field theory on the boundary. Different dimensions, same physics. One has gravity, one does not. The ADS-CFT correspondence. By 2015, this paper had more than 10,000 citations, most cited in high-energy physics history. The ADS-CFT correspondence guaranteed it, but how? How long before the information comes back out in the radiation? Their answer shocked everyone, very rapidly. After the Page time, quantum information deposited in the black hole appears in the Hawking radiation almost instantly. Before the Page time, information stays concealed. The black hole acts like a quantum information mirror with a delay controlled by scrambling time. Typical local quantum circuits are efficient encoders for quantum error correcting codes that nearly achieve the capacity of the quantum erasure channel. Translation: the chaotic dynamics inside a black hole naturally implement an error correction code. Not by design, not by fine-tuning, just by being a black hole that scrambles information maximally. The Hayden-Preskill protocol became a toy model, simple enough to calculate, rich enough to capture the physics. It proved you could retrieve information from something that looks like a black hole if you understand the code. Quantum field theory and curved space-time. No drama at the horizon. Pick two, give up the third. Quantum mechanics forbids maximal entanglement with two independent systems simultaneously. Monogamy of entanglement. Something must give. Ampius proposed that the entanglement between ingoing and outgoing particles breaks, violently. High-energy quanta at the horizon, a firewall. The infalling observer burns. The equivalence principle fails. No drama dies. Some for entirely new structures. Nobody liked firewalls. But nobody could show the argument was wrong. The paradox intensified. Quantum information theory and general relativity remained at war over the fate of information at the event horizon. But how does it encode information well enough to survive the chaos? Daniel Harlow started investigating the structure explicitly. The framework was already there. Quantum error correction, used in quantum computing to protect qubits from noise. The basic idea: spread logical information across many physical qubits, redundant encoding. When errors hit some qubits, measure syndromes, correct without learning the logical state. The no cloning theorem seems to forbid quantum error correction, but it does not. You can protect quantum information if you entangle it across many degrees of freedom without copying it. Measuring stabilizers reveals the error syndrome without collapsing the logical state. You correct, you recover. The most important family of stabilizer codes are CSS codes, Calderbanke-Shor-Steen codes, named after Robert Calderbank, Peter Shor, and Andrew Steen, who independently discovered them in 1996. CSS codes use two classical linear codes. One detects bit flip errors, one detects phase flip errors. Combine them into a quantum code that handles both. The 7-qubit Steen code is a CSS code. It encodes one logical qubit into 7 physical qubits and corrects any single qubit error. The mapping is holographic. Lower dimensional boundary encodes higher dimensional interior. In 2015, researchers started asking what kind of encoding this is. The answer was error correction. They showed that the ADS-CFT correspondence implements a quantum error correcting code. The bulk operators encoding interior information are protected against erasure of boundary degrees of freedom. Specifically, you can erase up to half the boundary and still reconstruct bulk operators in a certain region. That fraction, half, matches the threshold for error correction. Below half, the code works. Above half, information is lost. The threshold corresponds exactly to the Ryu-Takayanagi surface, a minimal surface in the bulk whose area computes the entanglement entropy of a boundary region. Holographic quantum error correction and the projected black hole interior. His claim was direct. Quantum error correction is essential for maintaining the smoothness of spacetime at the horizon. The code structure prevents firewalls. The entanglement between inside and outside is structured precisely like the entanglement in an error-correcting code. The code protects the interior state from errors caused by losing access to the radiation. This was not hand-waving. The mathematics was explicit. In Jacob-Teitelbaum gravity, a two-dimensional model, Almheri showed that after the page time, interior degrees of freedom are encoded in the Bath-Hilbert space. The encoding is correctable against quantum operations on the Bath that do not have prior access to black hole microstates and do not have large, negative coherent information. Published July 25, 2023 in Journal of High Energy Physics. The interior density matrix survives generic low-rank quantum operations. For erasure errors, gravity comes within an 0.1 factor of saturating the singleton bound. That bound sets the maximum fraction of qubits you can erase and still recover information. Black holes nearly achieve it. In ADS-CFT, every boundary region has an entanglement wedge in the bulk. The wedge is bounded by the region itself and by the Ryu-Takayanagi surface. Bulk operators in the wedge can be reconstructed from boundary operators in the region. After the page time, the entanglement wedge of the radiation includes the black hole interior. The interior becomes part of the code space accessible to observers holding the radiation. The island formula makes this precise. To compute the entropy of radiation, you extremize a generalized entropy that includes both the radiation region and an island inside the black hole. The island contribution appears after the page time. It is why the entropy decreases. The page curve emerges naturally. Entanglement wedge reconstruction and the information paradox. Ahmed Almheri, Netta Engelhardt, Don Meroff, and Henry Maxfield published Archiv Patars 1911. Toip 3 in JEP. Replica wormholes and the entropy of Hawking radiation. They use the gravitational path integral with replica tricks, summing over different spacetime topologies, wormholes connecting replicas. The dominant saddle point after the page time includes these replica wormholes. They carry the information that makes the page curve decrease. The calculation reproduced the page curve in models where you can compute everything. JT gravity coupled to a bath, eternal black holes in ADS space with a transparent boundary. The entropy followed the curve predicted by Page in 1993. It is de Sitter, or approximately flat. Does the resolution carry over? The consensus is yes. The lesson about quantum error correction and entanglement wedges is expected to generalize, but explicit calculations remain difficult. The breakthrough was showing that it works in tractable models. Once you see how nature solves the paradox in one setting, you understand the mechanism. If you value document physics and information theory like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the journal Nature Physics, published in August 2023, discussing holographic error correcting codes emerging from quantum gravity, and from Quantum Magazine, November 10, 2023, detailing how Ahmed Almheri and colleagues used error correction principles to prevent firewalls at black hole horizons. These sources compiled decades of research with specific technical results. Now back to the information. In the Hayden-Preskill protocol, the black hole evolution is modeled as a Haar-random unitary acting on the black hole plus the newly infalling information. This scrambles maximally. It encodes the information in the most generic possible way. The decoding problem becomes, given the radiation and some reference system that tracks what fell in, recover the input state. Yoshida and collaborators publish a breakthrough, decoding general error, correcting codes, and the role of complementarity. They extend CSS decoding circuits to handle non-stabilizer codes. The key is a pair of classical quantum codes associated with the quantum code. The decoding error depends on the classical decoding errors of these CQ codes and their degree of complementarity. They demonstrate this on the Hayden-Preskill protocol. The classical to quantum decoder achieves the quantum capacity of the protocol. It improves on previous decoupling analyses. The result shows that black hole dynamics optimally encode quantum information, but poorly encode classical information. Quantum data survives, classical data degrades. The complementarity between the two bases of the CQ codes is fundamental to making the decoding work. Start with an n-qubit black hole in some initial state. It is entangled with a reference system representing past radiation. Throw in a k-qubit message entangled with another reference. The black hole and message together form an n plus k qubit system. Apply a random unitary. This models the scrambling dynamics. Split the output into two parts. N plus k minus L qubits stay in the black hole. L qubits radiate out. If L is large enough and you have access to the old radiation, you can decode the message from the new radiation. The threshold is roughly at the page time. Before that, the code does not work. After that, information pours out. Black holes do none of that. They just evolve under Hamiltonian dynamics. Chaotic mixing. The scrambling itself creates the error correction structure. Fast scramblers saturate a bound. Scrambling time proportional to the logarithm of the entropy. Black holes achieve this bound. They scramble as fast as quantum mechanics allows. This maximal chaos is what makes them optimal quantum codes. The butterfly effect in black holes quantifies scrambling. Out-of-time order correlators, OTOCs, measure how much a local perturbation spreads across the system. In strongly chaotic systems, OTOCs decay exponentially with a rate called the Lyapunov exponent. Black holes have the maximum Lyapunov exponent allowed by quantum mechanics. That maximum was conjectured in 2017 by Maldacena, Schenker, and Stanford. It sets a speed limit on quantum information scrambling. Black holes sit right at the limit. This is not a coincidence. The same dynamics that make black holes scramble maximally also make them encode information optimally. They generalize classical linear codes to the quantum setting. Parity checks become stabilizers. Measurement outcomes become syndromes. The key property is that stabilizers form an abelian group. They all commute. This makes syndrome measurement non-destructive. You learn about errors without disturbing the logical state. For black holes, the stabilizers are not explicitly written down. The theory is not that clean, but the structure is there implicitly in the entanglement pattern and the holographic mapping. Gauge transformations that should be pure gauge in the bulk correspond to stabilizers on the boundary. They generate the code space. Physical states are those invariant undergauge transformations. This ties quantum error correction directly to gauge theory and gravity. Perfect tensors are special. They have a property called maximal entanglement. Cut the network in different ways, and the entanglement entropy is always determined by the minimal cut. Perfect tensors are isometries up to a permutation. They map smaller Hilbert spaces into larger ones, preserving all information. Holographic codes are built from perfect tensors. The bulk-to-boundary mapping is a tensor network where each layer is built from perfect tensors. This network defines the error-correcting code. Errors on the boundary correspond to cuts in the network. As long as the cut is not too large, the bulk information is recoverable. 5 tensors connected in a pentagon. Tessellate them to fill a hyperbolic space. The result is a quantum code where the code space has geometric properties. Bulk operators are simple on the boundary. Boundary operators restricted to code space are complicated in the bulk. The minimal surface dividing regions corresponds to the error correction threshold. You can erase everything on one side of the minimal surface and still recover bulk operators on the other side. This is exactly the property needed to avoid information loss in black holes. They are the same phenomenon seen from different angles. Holography encodes bulk geometry and boundary entanglement. Error correction protects logical information through redundant entanglement. Both use entanglement structure to make more with less. Bulk spacetime emerges from boundary entanglement. Logical qubits emerge from physical qubit entanglement. The mathematics is parallel. The firewall argument assumed that the entanglement between ingoing and outgoing Hawking modes is independent of the entanglement between early and late radiation. But in an error-correcting code, these are not independent. The late radiation is entangled with early radiation, because both are part of the boundary encoding of the bulk. The outgoing mode is entangled with the ingoing mode because they are part of the same bulk operator. The code structure reconciles both entanglements. No monogamy violation, no firewall. The equivalence principle survives because the quantum state at the horizon is structured to maintain smoothness. Error correction is not just a technical trick. It is the physical mechanism that allows black holes to have smooth horizons while preserving information. The exact fraction of boundary degrees of freedom needed to reconstruct the bulk is not random. It is 3/4. Slightly more than half is insufficient. This threshold comes from the code parameters. For a CSS code protecting k logical qubits using n physical qubits, the number of stabilizer generators is roughly n minus k. You need at least n minus k qubits to measure all syndromes and correct errors. For holographic codes, n is the boundary entropy and k is the bulk entropy. The ratio depends on the geometry. For black holes, the calculation gives 3/4. This is why you need access to 3/4 of the radiation to decode the black hole interior. The remaining quarter is insufficient because the code cannot correct that many erasures. Amit Almheri stated in interviews that the need for 3/4 says something important about quantum gravity. Why that fraction? The answer is not fully understood. It relates to the dimension of spacetime, the structure of entanglement, and the capacity of the quantum erasure channel. The singleton bound provides an upper limit. A code protecting k logical qubits against d erasures on n physical qubits satisfies n minus k is greater than or equal to d. For maximum distance, n minus k equals d. The bound is tight. Black holes nearly achieve it. Gravity saturates quantum information limits. This is not expected from classical reasoning. It emerges from quantum gravity dynamics. After the page time, the code space includes the island. The entropy decreases. The transition happens when the generalized entropy with the island becomes smaller than without it. The island formula extremizes over configurations. Two saddles compete. Early time prefers no island. Late time prefers island. The transition marks where the island saddle dominates. This is exactly a phase transition. Discontinuous derivative. Change in symmetry. In the language of quantum error correction, it is when the code activates. Before page time, errors accumulate. After page time, the code corrects them. The black hole switches from information loss regime to information recovery regime at the page time. The entropy. This is short. For a solar mass black hole, roughly microseconds. For a supermassive black hole, longer, but still short compared to evaporation time. The point is that once information enters, it scrambles fast. The Hayden-Preskill protocol says that after scrambling, information leaks out rapidly. The delay is scrambling time. The recovery is fast. This seems paradoxical. Information goes in, scrambles, becomes thermally distributed, yet still comes out intact. The resolution is error correction. The thermal appearance is in the coarse-grained description. The fine-grained information is in the entanglement pattern. The code hides information in correlations invisible to local measurements, but recoverable with global access. But we can simulate the dynamics. Quantum computers running the Hayden-Preskill protocol, spin chains implementing scrambling Hamiltonians. Experimental realizations were published starting 2019. Researchers constructed analog black holes using spin systems. They threw in quantum information. They measured how long until it emerged in the radiation. The results matched the theoretical predictions. Information did emerge after scrambling. The protocol worked. This does not prove that real astrophysical black holes preserve information, but it shows that the mechanism is physically realizable. The math works in practice, not just on paper. The fact that distant regions are independent is because the code space factorizes. Geometry is a consequence of how information is encoded. This is radical. We usually think of geometry as fundamental. Points, distances, curvature. But in quantum gravity, geometry might be derived. An effective description of how quantum information organizes itself. Spacetime is not a stage where physics happens. It is a pattern in the quantum state. When the pattern has the right structure, we see smooth geometry. When the structure breaks down, spacetime becomes fuzzy or fails. The code distance is the size of the smallest error that cannot be detected. You make the lattice bigger, the code distance grows, the logical error rate drops exponentially. The idea is that by arranging qubits in the right pattern, you make a robust quantum memory. AddSCFT says nature does something similar. Arrange quantum degrees of freedom on a boundary in the right pattern. You get a bulk spacetime that resists information loss. The black hole horizon is like a topological code boundary. Errors in the bulk correspond to excitations on the boundary. The code structure prevents them from destroying information. If spacetime is emergent from entanglement, the gravitational interaction is a residual effect of the entanglement structure. It is not a fundamental force. It is the way matter couples to geometry. Geometry is just the pattern of entanglement. Weak coupling corresponds to large code distance. The bulk is well separated from the boundary. This separation is why gravity appears weak. Entanglement is strong. Gravity is weak. They are dual descriptions, but it shows that quantum error correction ideas can address questions beyond black holes. The framework is general. Any system where information must survive chaos or erasure might use similar mechanisms. Neural networks, biological systems, evolution. Information storage in any noisy environment has error correction structure. Nature knows how to do this. We are just learning the math. The recent progress on the page curve calculation is not the end. It is a beginning. We reproduce the curve in simplified models. JT gravity, 2-dimensional. Add S space. Evaporating black holes in our universe are 4-dimensional. Schwarzschild or Kerr geometry. No exact holographic dual. Can we calculate the page curve there? Partial results exist. The methods are harder, but the principles should apply. If quantum gravity is unitary, the page curve must appear. Error correction must operate. The details differ, but the structure persists. How does the code protect against specific error types? These are technical questions with practical implications. If we knew the code, we could simulate black hole information dynamics exactly. We could test predictions in quantum computers. We could probe quantum gravity without building a collider at the Planck scale. Different black holes have different entropies, different scrambling times, different page times. Does the code family change? Kerr black holes have angular momentum. The information dynamics should differ from Schwarzschild. How? The page curve for Kerr black holes was computed numerically in 2024. It follows the same qualitative shape, but with different timescales. The page time depends on the angular momentum parameter. Fast-spinning black holes have shorter page times. The code capacity adjusts to the available entropy. The mechanism is flexible. The entropy saturates the extremal entropy rather than decreasing to zero. The code still works, but the endpoint is different. The extremal case is like a quantum memory that never fully erases. It reaches a minimal entropy state and stays there. The information is stored indefinitely. This has implications for remnants. Maybe extremal black holes are stable information storage devices in quantum gravity. Black hole complementarity gets a new interpretation. Complementarity says that an infalling observer sees nothing unusual at the horizon, while an external observer sees information thermalize and escape. These seem contradictory. Both cannot be real. But in quantum error correction terms, they are different perspectives on the same code. The infalling observer sees the logical state, smooth, unitary. The external observer sees the physical encoding, thermal, entangled. Neither is wrong. They are complementary descriptions like position and momentum. The code allows both to be true because the encoding is non-local. Information is not in the Hawking particles. It is in the pattern of entanglement between particles. Local measurements see thermal noise. Global measurements see pure quantum state. No contradiction, just complementarity. The ER equals EPR conjecture by Maldacena and Suskind fits here. ER is Einstein-Rosen bridges, wormholes. EPR is Einstein-Podolsky-Rosen pairs, entangled particles. The conjecture says these are the same. An entangled pair is connected by a wormhole, not a traversable wormhole, a geometric feature in the spacetime. Entanglement creates geometry. If true, quantum error correction explains how. The wormhole is the geometric representation of the entanglement in the code. The code space has a bulk description where entangled regions are connected by minimal surfaces. Those surfaces are wormholes in the geometry. The information travels through the wormhole, in the sense that it is encoded in the entanglement that the wormhole represents. This is not science fiction. This is mathematical structure in ADS CFT. The firewall debate is not settled. Some physicists still argue that quantum error correction is not sufficient. There are assumptions in the argument. The decoding must be efficient, polynomial time in the entropy. If decoding requires exponential time, it is not physically accessible. Daniel Harlow and Patrick Hayden argued in 2013 that the AMPS experiment requires quantum computations exponential in black hole entropy. Such computations take longer than the age of the universe for macroscopic black holes. If the experiment cannot be done, the firewall is not physical. It is an artifact of idealized assumptions. Quantum error correction supports this view. The code prevents the firewall by making the dangerous operations computationally inaccessible. Maybe advanced civilizations can perform these computations. Maybe quantum computers of the far future. This does not change the physics, but shifts the burden. If firewalls require exponential resources to observe, they are not a practical problem. Black holes remain smooth for realistic observers. The error correction structure ensures this. The code is not perfect, but it is good enough. Typical errors are correctable. Atypical errors that break the code are exponentially rare or exponentially hard to engineer. This pragmatic approach is unusual in fundamental physics. Usually the application comes decades after the theory. Here, the theory and application develop together. Quantum computing needs error correction to work. Black holes use error correction to exist. Study one, learn about the other. Quark gluon plasma. These systems have quantum entanglement at macroscopic scales. Traditional methods fail to calculate their properties. Perturbation theory breaks down. Numerical simulation becomes intractable. ADS CFT provides a tool. Map the strongly coupled quantum system to a weakly coupled gravity theory. Solve the gravity problem. Translate back. This works if the system has a holographic dual. Not all do. But for those that do, you gain insight. Quantum error correction structure in the dual gravity theory tells you about the information flow in the original quantum system. Thermalization, transport, chaos. The same quantities that matter for black hole information appear in condensed matter. The same string theory that attempts to unify gravity and quantum mechanics also describes the low energy behavior of certain quantum field theories. The duality is exact at strong coupling. You can compute transport coefficients in a quark gluon plasma by solving Einstein's equations in a curved spacetime. The viscosity over entropy ratio reaches a universal lower bound. Black holes saturate the bound, so do strongly coupled quantum systems. The bound is fundamental. It relates to how fast information spreads. This is scrambling. Fast scrambling means low viscosity, efficient transport. The quantum error correction structure in the gravity dual governs these properties. The breakthrough papers in 2020 did not come from nowhere. They synthesized tools from quantum information theory, holography, replica tricks, and gravitational path integrals. The path integral approach sums over all possible spacetime geometries weighted by the action. In replica calculations, you compute powers of the density matrix by considering multiple copies of the system. The dominant saddle points in the path. Integral correspond to different geometries. Some involve wormholes connecting the replicas. These replica wormholes encode the quantum information that makes the entropy follow the Page curve. The generalized entropy is the area of the boundary of I in Planck units plus the von Neumann entropy of matter fields on R union Y. Extremize over all possible islands. Take the minimum. Before the Page time, the minimal configuration has no island. The formula reduces to ordinary entropy. After the Page time, an island appears inside the black hole. The area term contributes the Bekenstein-Hawking entropy of the remaining black hole. The matter entropy term becomes small because R union I covers most of the global state. The total decreases. The Page curve emerges. The island is not a new ingredient added by hand. It is the dominant saddle point in the quantum extremal surface calculation. It emerges from the gravitational path integral when you include quantum corrections properly. Any system with a region that is difficult to access and a region that is easy to access can have islands. The inaccessible region is like the black hole interior. The accessible region is like the radiation. If the two are entangled properly, islands can form. This happens in models of quantum cosmology. The early universe behind our cosmological horizon, we cannot see it, but it is entangled with the observable universe. Islands appear in the path integral. They contribute to the entropy of the observable region. This suggests that information about the early universe is not lost. It is encoded in our Hubble volume in a subtle way that requires quantum error correction to decode. This is speculative, but it shows how the ideas generalize. It says the entanglement entropy of a boundary region in a CFT equals the area of a minimal surface in the at-s bulk divided by 4 times Newton's constant. This connects quantum entanglement to geometry directly. It was a major insight into holography. The island formula is the quantum corrected version. The minimal surface is replaced by a quantum extremal surface. The area remains, but matter entropy adds. The two formulas agree in the classical limit. When quantum corrections are small, the area term dominates. When quantum corrections grow large, matter entropy matters. This transition is the Page transition. Operators in the wedge can be reconstructed from operators on the boundary. This is a precise statement about quantum error correction. The boundary encodes the wedge. Lose part of the boundary, lose part of the wedge. But as long as enough boundary remains, the wedge is recoverable. After the Page time, the entanglement wedge of the radiation includes the black hole interior. The interior is part of the code space. Observers with access to enough radiation can decode the interior. This resolves the paradox. Information never fell into an inaccessible region. It was always encoded in the accessible region. We just needed the right code to see it. The scrambling is as fast as possible. The recovery after Page time is rapid. If you wanted to design a quantum memory in a universe with gravity, you would design something like a black hole. Nature already did. This reverses the intuition. We thought black holes destroy information. They preserve it better than almost anything else. The paradox was our failure to see the code. Now, let us state what we know with certainty versus what remains conjecture. We know quantum mechanics is unitary. Every controlled experiment confirms this. We know general relativity describes gravity accurately in regimes we can test. We know ADS CFT correspondence works in many examples. We can calculate both sides and they agree. We know quantum error correction is mathematically sound. It is used in real quantum computers. We know the Hayden-Preskill protocol works in simulations. We know the Page curve was reproduced in models where everything is calculable. These are facts with backing. Supermassive black holes evaporate too slowly. We cannot perform the AMPS experiment. We cannot measure the fine-grained entropy. We rely on consistency. If the theory is right in all the places we can check it, we trust it in places we cannot. This is how theoretical physics works. Extrapolate from known to unknown guided by principles. Unitarity, locality where possible, holography, Error correction. These are the principles that led to the current picture. If one fails, the edifice cracks. So far, none have failed. Understand the 3/4 threshold from first principles. Explore what quantum error correction implies for emergence of spacetime. Connect to observable predictions, maybe quantum gravity effects and gravitational wave signals, maybe subtle correlations in cosmic microwave background, maybe something entirely unexpected. The theory has predictive power. We need experiments to test it. Some critics argue the entire program is too removed from observation. String theory has no direct tests. ADIA-SOC CFT works in a universe we do not live in. Quantum error correction is imported from quantum computing. Where is the contact with reality? The response is that internal consistency is evidence. Mathematics does not lie. If the same structure appears in quantum gravity, holography, quantum information, and condensed matter, it is probably real. The universe is under no obligation to be simple, but it is under obligation to be consistent. Quantum error correction provides consistency. It reconciles gravity and quantum mechanics in regimes where both matter. That is evidence. Nature encoded it in the structure of space-time. Every black hole runs the algorithm. Every horizon preserves information. Every bit that falls in comes back out in the Hawking radiation, given enough time and the right decoding. This is not philosophy. It is physics with equations, proofs, and specific calculations that reproduce the page curve from first principles, using the gravitational path integral with replica wormhole geometries and quantum extremal surfaces. The papers are on AR6EV. The results are peer-reviewed. The community is converging on this picture. The transition point where the island appears is where the code distance of the holographic code crosses the threshold needed to correct the errors induced by radiation loss. This is not a separate result. It is the same result viewed through the quantum information lens. The page time is the error correction activation time. The island is the code space. The radiation is the syndrome. The black hole interior is the logical information. Every piece maps to error correction terminology. The paradox dissolved because we finally learned to speak the right language. Information was never lost. It was encoded. We just needed to see the quantum code hidden in the quantum geometry, written in the quantum entanglement between space and time. Billion years old, the same mathematics, the same structure, the same solution to the same problem. How do you preserve information in a chaotic environment where everything wants to destroy it? You spread it, entangle it, encode it, check it, correct it. Nature knew this before we did. Black holes implement the code without circuits or programmers, just gravity, just quantum mechanics, just information, finding a way to survive against entropy and chaos and the heat death at the horizon, where space-time curves so steep that light cannot escape. But quantum information still does, through the thin thread of entanglement connecting the inside to the outside in a pattern so subtle that it took us 40 years to notice it was there all along, staring at us from the event horizon of every black hole in every galaxy, encoding every bit that ever fell in, waiting for us to decode it and read the message that information is not lost, it is just hidden in the code.